Well, we made it. As exciting as Module 1 was, Module 2 is where the fun truly begins. It is here, in Module 2, Control Strategies, where you will learn some of the more common HVAC system configurations you will encounter on your base and the most appropriate way to control them. This module starts out with a hydronic systems overview. Some of the material covered here may be a repeat from the Introduction to Mechanical Systems course, but it will be presented in a different way to further provide you the opportunity to really learn this stuff. As I have said before, to truly understand HVAC controls, you have to have a very good understanding of the intent of the engineer who designed the system you are trying to control, and vice versa. To be a good design engineer, you need to be thinking about how your system is going to be controlled across a spectrum of scenarios it will encounter. In this lesson, we will talk about some typical hydronic system layouts, but present them from a perspective which looks at the advantages and disadvantages the various layouts present in regards to the controllability of such systems. The objective for this lesson will be for students to comprehend the functions of the major components of hydronic systems, as well as understand the benefits and limitations of various piping and pumping configurations. The corresponding samples of behavior will be: describe the best location for an air separator in a hydronic system. State the general relationship between pressure drop and flow through a hydronic system. Differentiate between system and pump curves. Distinguish between different piping configurations. Describe the implications an unbalanced hydronic system will have on the controllability of such a system. And distinguish between different pumping configurations. Alright, first things first. What do we mean by a hydronic system? A hydronic system is just a piping system that moves water, or a water-glycol mixture. This water, or water-glycol mixture, is just the medium we use to carry heat to or from a load. For instance, in a hot water system, we heat up water with either a boiler or a steam-to-water heat exchanger, and then we pump that water through pipes to various loads, or locations that are in need of heat. The heat is given off via some sort of heat exchanger. Some common examples of heat exchangers would be a heating coil, like those located in your air handling unit or VAV box, a fan coil unit, or a radiator. Since the water gives off heat at those locations, it drops in temperature. We then need to bring it back to the heat source, for example the boiler, to heat it up again and start the process all over. Chilled water systems work in a very similar fashion, except they are absorbing heat from the building, which is typically done at the cooling coil located in an air handling unit, and are bringing it back to a chiller to extract that heat, or said another way, chill that water down again so the cycle can repeat itself. When working through different system configurations in the lessons of this module, it is always important to follow the heat. For heating systems, how is the heat getting from the generation location to the space where it is actually needed? For cooling systems, how is the heat being removed from the space and eventually transferred outside to be expelled to the environment? Hydronic systems are just a piece of that puzzle. They move the heat around by absorbing it and expelling it at different locations. The concept sounds easy enough, but hydronic systems actually have a lot of components and can come in a variety of different layouts. Let's start our deep dive into these systems by taking a look from the schematics perspective. We need to start simple and work our way up. Shown here is a simple schematic of a hot water system like we were just talking about. We will try to be as consistent as possible with the symbols used to denote the different components of HVAC systems throughout this course. Starting on the right-hand side, we have the load. Now, what do we mean by load? It can be thought of as a heat exchanger. This term load comes from the fact that these heat exchangers carry with them some heating load, or heating requirement, measured in BTUs per hour, that they have to provide. Again, the most common heat exchangers for such a system would be heating coils in air handling units or VAV boxes, fan coil units, and baseboard radiators. Hot water is flowing through that coil, and when it does that, it gives off heat, usually to an airstream. So, as the water gives off this heat, it is cooled down a few degrees. After the load, the water will flow through some piping back to the boiler where it is again reheated, typically by some sort of combustion process occurring inside the boiler. The heated up water then makes its way towards a device called an air separator, denoted AS here on the schematic. The air separator is a device which removes air that is entrapped in the water. We will discuss this device and why it is required in a little more detail here in just a minute. Then we have a component of the hydronic system called the expansion tank. Depending on the style of expansion tank, sometimes it is piped into the top of the air separator. The expansion tank is where we allow the water to expand into. When this system is filled, we typically fill it with water from the domestic water supply. That is the same cold water that runs out of bathroom faucets, and it is typically around 50 to 60 degrees Fahrenheit. When we fire up the boiler, we are often running at temperatures on the order of 200 degrees Fahrenheit. As water is heated up, it expands. It doesn't expand a ton, but enough that if we didn't have a place for it to expand into, that is the expansion tank, it may burst some pipes. Expansion tanks also serve as a safety mechanism for the system. Oftentimes, there's a diaphragm separating the water inside of the tank from some other pressurized gas. We can charge that gas to a certain pressure to ensure there's always sufficient enough pressure on the inlet side of the pump to prevent what is known as cavitation. Cavitation is something that can occur in our remaining component of this hydronic system, the pump. Pumps are the devices used to move the fluid. As the water whips around the inside of a pump, there are locations inside of the pump where the static pressure of the water can drop to a point where it is at risk of water evaporating from the liquid state into a gaseous state. Eventually, those water vapor bubbles will encounter a location in the pump where the static pressure is a little higher, and those bubbles would subsequently collapse. The process of evaporation and then collapsing is referred to as cavitation, and it can be very damaging to pumps. It's like mini implosions occurring inside the pump. These implosions emit high-intensity shock waves, and such shock waves can damage components of a pump, in particular the pump's impeller. Thus, we always want to ensure a significant amount of pressure on the suction side of the pump is present, since it's harder to evaporate water at higher pressures. We ensure that appropriate amount of pressure is maintained on the suction side by having the expansion tank located where it is, right before the pump. It could be put elsewhere, but the engineer better know what he or she is doing. So in essence, the expansion tank is kind of a control device. It ensures minimum required pressures are realized in the system to ensure the system operates as designed. Additionally, there is typically a pressure relief valve located in the piping leading to the expansion tank, which will bleed off pressure if it begins to get too high. Let's compare this simple diagram of a hot water system with a similar diagram of a chilled water system. Aside from the fact that we replaced the boiler with a chiller, we have all the same components. However, their locations with respect to each other have changed a bit. In particular, the air separator and expansion tank are still on the suction side of the pump, but now the pump is before the chiller. In a hot water system, the pump comes downstream of the boiler. The reason for this discrepancy here comes from the required location of the air separator. You see, the air separator needs to be placed in a location in the piping system where the water is trying to get rid of excess and trapped air. Water can and will always hold a certain amount of air. That is how the air got into the piping system to begin with. When the system was filled with the domestic water supply, that water contained some air dissolved inside of it. When the pressure of water drops, or its temperature is increased, the amount of air that can stay dissolved in the water decreases. The plot shown here depicts this. Imagine in the hot water system, we charge our expansion tank to 15 psi on the suction side of the pump. Say that system is initially filled with 60 degree Fahrenheit water from the domestic water supply. For that temperature and pressure, the solubility of air in water is 4% air by volume. Once we turn on the pump and boiler, the pressure at that location will increase a bit. Let's say to 30 psi, because the water is expanding a bit when it is heated. The temperature will increase to somewhere around 200 degrees Fahrenheit. So going up on that plot from where we started, we find that for 200 degrees Fahrenheit and 30 psi, now the solubility has decreased to something on the order of 2.5%. That means we could literally have air bubbles in our pipes at a location with that temperature and pressure. That would be a great location to put the air separator, because the air is already separated. We just need to give it room to escape the piping system. It looks as though the solubility of air in water has a stronger dependence on pressure than it does on temperature. Therefore, we need to ensure that we have our air separator be located before the pump in both the hot water and chilled water systems, because that is where the pressure in the hydronic system will be the lowest. We would also like to place the air separator at a location where the temperature is the highest. In a hot water system, that would be after the boiler. In a chilled water system, the water temperature would be the highest after the cooling coil, but before the chiller. Therefore, the schematics shown here are the best arrangements for reducing air in the system. That is not always the case for existing systems, but whenever possible, new construction should be following this arrangement. Now, there may be a few exceptions to this rule. For instance, if you have a hot water pump and boiler located on the first floor of a building, and your common return piping headed to the boiler is coming from the top floor, the lowest static water pressure in your hot water system may actually exist in the return piping located on the top floor. Static pressure builds as you drop in elevation of a building. This is due to the weight of water. In such an instance, it may be better to locate the air separator at the top floor, upstream of the boiler, for it to be most effective in removing air from the system. Bottom line, always place your air separator in the location of your system where the pressure is the lowest and the temperature is the highest. You may want to stop here and rewind this recording if need be. We know we just threw a lot at you. So we talked about the best locations for the air separator, but why do we care to remove air at all? Well, if pockets of air enter the pump's impeller will experience a sudden drop in force acting on it, since it is going from pushing water to pushing air. It is like when you're paddling a canoe. If the paddle comes out of the water sooner than you expect, the paddle speed will increase, and you might fall forward. In a pump, encountering such pockets of air will free spin the impellers for a moment before they catch up to more water. This free spinning can jolt the pump, which can damage it, but it will also lower the efficiency of the pump. So in essence, the air separator is also kind of a control device. It is controlling the amount of air in the system to ensure the system operates correctly. Additionally, air in the system can escalate the rate of corrosion on the inside of the pipes. We've also listed some additional issues that come from having air in your hydronic system, and we will let you investigate those further if desired. Before we continue in our discussion on pumps, let's talk a little bit about the relationship between pressure and flow. In a hydronic system, as the water flows through the pipes, fittings, valves, and other devices like the air separator and coils, there will always be a drop in pressure. Say you want to push a certain flow rate, maybe 100 GPM through your piping system. There's going to be pressure drops in the water as the water flows through each length of pipe, through each fitting, valve, device, and coil. The total pressure drop from the pump discharge to the pump inlet would just be the sum of all those individual pressure drops. Now, say you actually wanted to double the flow to 200 GPM, but nothing in the system configuration is allowed to change. That is, you will keep the same size pipes, valves, fitting, etc. Increased flow will result in increased pressure drops through each of those components. And the relationship between those two parameters is as follows. The pressure drop throughout the system is proportional to the square of the volumetric flow rate of water. Said another way, it is equal to some constant K multiplied by the square of the volumetric flow rate. The value of K will be dependent on the size and layout of the hydronic system. Graphically, this relationship looks like this. This curve is called the system curve. It is always a squared relationship, but again, the rate at which the pressure increases with increases in flow depends on the system. That is, each system layout will have a different value of K in the equation shown here. So say we have two hydronic systems, which are laid out in the exact same way, but the only difference is the pipes in the second system are a size smaller, maybe 2-inch diameter instead of 3-inch diameter. This would be a more restrictive system, since it is harder to push a certain flow rate through smaller pipes than it is to push that same flow rate through larger pipes. Just think of trying to suck down a Coke through a coffee stirring straw versus trying to suck it down through a larger straw. You don't have to work so hard to drink it through the larger straw. Thus, a comparison of these two systems' pressure to flow relationship would look like this. The more restrictive system would be the one with the smaller pipes, and it subsequently has a larger K value. Now, you don't have to change the diameter of pipes to change the shape of the system curve. It would change if you started to restrict flow to the coil by closing the control valve at that load. So, in most hydronic systems we encounter, the system curve is often changing, but we will save that discussion for the next lesson. Alright, the last component of these simple hydronic systems we have been looking at is the pump. The pump is the device that increases the pressure in the system, which will subsequently drive the flow of water through the system. The amount of pressure increase they have to add to the system will be equal to that of all the pressure drops in the rest of the system. Different pumps have different operating characteristics. That is, the pressure increase they provide to the system will depend on the flow rate they are pushing. These operating characteristics are best represented by looking at pump performance data. These plots are supplied by the pump manufacturer and have a lot of information on them. We will not talk about every bit of information on them in this lesson. We will save some of those discussions for the next lesson. This is the pump performance data for a Bell & Gossett E1510 series pump with the model number 2ADES. There are a lot of lines here, but let's focus in on those that start horizontally on the left side of the plot and start to slope downwards as you follow them to the right. These curves are termed pump curves. There are several of them for different impeller size options. Let's just focus in on the top one for a 7-inch impeller. If the pump is going to operate in a constant speed scenario, in this case at 1750 RPMs, the pump will operate on this pump curve. Where exactly on the pump curve it will operate will solely depend on the system it is installed in. The point of operation will be the intersection of this pump curve with that of the system curve. Now you might be saying, hold on, the pump curve's vertical axis is total head measured in feet, but I thought it should be pressure. Well, feet of head actually is a measurement of pressure. It is the pressure that results from being underneath a column of water so many feet high. For example, say a pump puts out 42 feet of head pressure at 150 GPM of flow. That means the pressure increase the pump puts into the system is equal to the same amount of pressure you would feel 42 feet below the surface of a lake. So that is how it works. The amount of flow that the pump can push through a particular system can be found by plotting the system curve on top of the pump curve and find where those two curves intersect. The pump will always operate on its pump curve. If the system has valves opening and closing, the system curve will change, and thus the intersection of the pump curve and system curve will change as well. But as long as the pump remains at 1750 RPM, that operating point will stay on the pump curve, which does not change. We will discuss the effects of variable speed pumps in a couple lessons from now. The only other information on this performance data we want to point out now is that of net positive suction head. It is shown on this curve here, and you actually need to read off its value on the right-hand vertical axis. This value is just stating the minimum required pressure that needs to be maintained on the suction side of the pump to ensure cavitation does not occur. How do we ensure this minimum pressure is maintained? As discussed before, we can set that pressure by use of the expansion tank. We just have to charge that tank to ensure the pressure in the system on the suction side of the pump is maintained above this minimum for the location on the pump curve that the pump is operating at. Alright, so we have covered all the major components of simple hydronic systems. There are other components that we didn't show here, like all the valves, strainers, pressure gauges, etc. We will get there when we get there. For now, if you are comfortable with the general layout and the components thus far discussed, you are on the right track. A lot of hydronic systems you all will be dealing with already exist. You can learn a lot about those systems by just tracing the pipes throughout the mechanical room and building. In fact, I encourage you to do this as much as possible, but it's not always possible. These pipes may be running through areas you can't access for one reason or another. Thus, you need to be comfortable reading as-built drawings, which provide a wealth of information about the system. We can't afford to dive too deep into drawings, but we think it is important to at least tell you where some of the information you may want to find would be located in them. First off, the general layout of the hydronic system usually has its own dedicated drawing in the set of as-built drawings. For larger buildings, there may be one such drawing for each floor or wing of a building. This drawing is often called the HVAC piping plan or just piping plan. It will be in the mechanical section of the drawing set. Thus, its drawing number will have an M in front of it. This general layout of the piping system is shown here, but there often lacks much detail. For instance, there may be many pipes and components located in close proximity to each other in a mechanical room. So there might have to be a separate drawing or detail which shows in more detail what pipes and equipment are located in there. Here is that more detailed drawing of the particular mechanical room we were looking at. Still, there's often not enough information on such drawings. There's often a piping schematic for each hydronic system located on another drawing sheet. That such drawing might be labeled pipe schematics, or those schematics may be found as details on a mechanical schedule sheet or a control sequences sheet. These schematics are not to scale, but they provide a good reference to the installing contractor and for you after construction of how the systems are supposed to be laid out. That is, where in reference to each other are the major components of the system being placed. Just because we showed you that the air separator is best to be placed on the suction side of the pump does not mean that every hydronic system out there exhibits this practice. The engineer may have good reason to put it elsewhere, or maybe he just hasn't taken such a sweet class like this. There's also usually a sheet labeled mechanical details, or something to that effect. That sheet would contain a bunch of detailed schematics showing how the various components of the system, like the coils and air separator, are to be piped in. And lastly, there are the mechanical schedule drawings. These are usually an arrangement of tables that have detailed information about all the various devices in the hydronic system. There may be a schedule for all the air separators installed in the building, another one for the expansion tanks, and yet another one for all the pumps. This is all the time we can afford to go into the drawing sets for now, but I encourage you all to dive into drawing sets for the systems you are currently working on and learn how they are laid out and where to find various information that will help you in troubleshooting the systems you are dealing with. Thus far, we have looked at simple hot water and chilled water hydronic systems. These systems are said to be closed systems. The definition of a closed hydronic system is a system that has no more than one point of interface with a compressible gas, for example, the atmosphere, or a diaphragm. Regardless of the style of expansion tank used, inside the tank there is always such an interface. Again, it is at the interface where we can set the reference pressure for the system. There is also what we call open systems. These open hydronic systems are open to the atmosphere in more than one location. In HVAC applications, the most common example of an open hydronic system would be that of the condenser water loop, which brings warm air to the top of a cooling tower to be cooled down. Here, there are actually two locations where the hydronic loop is in contact with the atmosphere. Thus, at those two locations, the water is at atmospheric pressure. In a condenser water loop, those two locations would be at the top of the cooling tower, where the water is dispensed onto the fill, and at the bottom of the tower, where the water that is not evaporated pools up before it is sucked down a pipe back towards the condenser water pump. The issues with open systems, and condenser water loop systems in particular, is that there is dirt and other crap constantly getting into the hydronic system. Thus, appropriate treatment is required so that the stuff doesn't clog up our system and make it operate inefficiently. Additionally, in the case of the condenser water loop, water is constantly being evaporated out of the system as the stream trickles down through the cooling tower, and thus we need to replace such evaporated water. This constant introduction of makeup water from the domestic water source means that we're constantly bringing in more entrapped air. Oftentimes, an air separator isn't even placed in the system since it would just be fighting a losing battle. An additional issue that arises is the system now operates at higher concentrations of calcium and other minerals that are not evaporated when the water evaporates in the cooling tower. The last issue with open systems is there an increased risk of cavitation if the design engineer doesn't understand the added precautions that need to take place for open systems. Further discussion on that is beyond the scope of this course, but it is discussed in the HVAC design and analysis courses taught here at AFIT.